x0 to x0 plus delta x, and at the same time, the momentum of the particle is between p0 plus delta p, what you will do? Forget about what you need to multiply. You definitely need delta x and delta p here. Yeah? Delta x to keep the idea that the probability of finding the particle in the small region of the space is given by something multiplied to dx. And you need dp. Probability is probability. So when I'm looking for the NRS, is the same as I'm talking about the probability of finding the particle. So the momentum is going to get with this. So at the same time, you need the. So I want to tell you that even in quantum mechanics, if somebody asks this question for you, forget about what function you need to multiply, and we don't know that exactly. You needed dx and dp. So you need two index. And look at that. I want to back to here. So if you forget about the second index, this is what is this? It's a canonical ensemble. Huh? And the problem in canonical ensemble was that give me the probability of finding the particles, yeah, at the spatial temperature, a spatial probability. It looks like the exactly first equation I got. Give me the probability of finding the particle when the particle is sitting in this range of the x. Now I want more from you. I say that find the probability of finding. Next question. Give me the probability function of finding the particle at the spatial, not momentum, numbers. Because x here looks like the x, where e looks like the x for me, and it's similar. You know, just this is actually absolutely wrong if you want to relate these two equations together directly. Just to. Because you know that more or less better than this equation. So I use this example. So appearance of the two index, it looks like that. You are looking to find the quantum probability of finding a particle at the x and the p, in a small region. You know dx and dp is the phase space if they sit together. So it's the statistical physics actually. That was the reason that I take this. And in this approach, you don't have phase space. I know that you don't see the phase space. But these indexes play the role of the phase space for you. So this index can play the role of the coordinate x, for example, and this can play the role of vice versa. R, because R is related to the energy. It can play the role of the p, and it can play the role of the x, like the coordinate. As I told you, it's very hard to interpret this equation in the terms like what you have in the phase space, but it looks like very interesting actually. So this equation can be understood like what I explained in quantum mechanics actually. So, and what is this? You know, what's this equation? If I want to make interpretation for that in quantum mechanics, what I can say about this? If I want to find the equivalent equation for this is like this. What they call it, the normalization or the conservation of the probability. Another name for this equation is Parseval equality. Parseval. Oh, one thing I want to tell you, because this calculation is just 5 minutes, you know, I know what we will do, yeah? We'll make the variation from that. Let me to do that, and I will back to this because there is something here very interesting I want to tell you. This particle never will be lost in quantum mechanics. What does it mean? If you can find a particle in this spatial range of the x for me, with some probability, okay, this particle can be found in another range of the momentum also in the phase in the momentum space. I mean, if you track a particle if this is the x space, and if this is a p space, you are looking to find the probability of finding the electron, for example, in this range. So this is a psi x squared ax, delta x. If you can find this particle in this x, definitely if you change your language, you can say that you can find this particle in some type of the momentum range also, but with different amplitude. Different amplitude. For example, here the probability of the finding the particle is 0.25, for example, percent. For example, the same particle with this range of the x, you can find it here in the range of the momentum with the probability of 0.1%. Okay? But you can find. The probability will be different. But you know the total probability will be. So finally, if you change your range of the x, the probability of the finding the electron will increase, and here will be decreased or increase, we don't know. But the total probability is 1 and 1. I mean, no particle will be lost. Nothing will be lost here. So, I want to back to this variational calculation. So, if you make the variation from that, so variational n factorial pi rs n rs factorial minus beta sigma er delta n rs So this you know how to do. This will be the variation of this will be 0 because this is a constant minus variational this. Sorry, we need the logarithm of this because it's a big number. Logarithm. Minus the variational logarithm pi will be minus sigma rs variational n rs factorial. Just first term because the other terms are easy. They have nothing to do with them. They have nothing to do. Minus sigma rs. So we use here the Stirling approximation. I know that we need to be very careful about that, but anyway. I use the approximation Stirling here for the factorial. And make the variation from that. So minus sigma rs delta n rs. Just make the logarithm. Derivative. Differential this expression, you get okay. This is the total variation of the first term and the second term. So.
Plus what?
No. Why? No, because they cancel.
One cancel.
With that. Yes. So this variation, I told you I can't add something more here to this calculation because this mathematical calculation is same as we did in the canonical. finally we will have minus sigma delta n rs. So from first one will be remain ln n rs plus beta er. Okay. So this is like partial derivative as I told you. So it looks like delta xi fi xj 0 visual work. This is called the principal visual work also. I don't know. In the dynamics, one way to find the equation of motion is using the visual work. So for Lagrange mechanics also the same. So that should be the same. So the condition is that all the functions here should be 0. Fi xj equivalent to 0. So that will be equivalent to 0. So n rs will be proportional to exponential minus beta er minus 1. This is a proportional to and the probability, this is the NRS. We know that the sigma NRS will be total n. So this proportional, so you can write C exponentially this just by inserting proportionality constant here. So to find the C, you can use these expressions. So C will be n over sigma n. And finally, what you call it probability is, of course, this all are the maximum because you set this 0. So when you set the 0, you find this solution for the equation. Solution for this equation is given NRS equal to. You can forget about the star. Yes. I mean, this is one of the n, which gives you this sigma minimum or maximum. So will be NRS over n exponential minus beta. Okay, this is, you see that the difference of this with the canonical. So you can easily interpret the parameter of alpha and the beta. So just starting from the thermodynamics equations, you can see that the beta is related to the average of the energy because you need to find the mean of the alpha and beta. So meaning alpha and beta. So average of the energy is sigma ERNRS. Okay, this is a question I can write minus partial beta logarithm sigma just take the derivative of the logarithm. You will see that. You know what is that? It looks like exactly the partition function. So everything is repeated from the. So this is actually the partition function, yes? Q. Partition function. We don't say this Qn because you have not alpha also, you have also alpha here, 2 parameters. Huh? Okay, it's very common to define a function, we call it ground canonical partition function. Instead of the Q, because Q with 2 parameters is not common. We use it before Q with 1 parameter. When you have an alpha here, I want to define the nu. This is what call it d alpha and that. Grand canonical. And we define Q as a LND. Yes. So average of the energy, you can write minus 1 the Q here for the metal. And you can write all the thermodynamical equation like the pressure and these things like that. Okay, so you see that the beta is related to the average of the energy, so it's the same beta as you have in the statistical, in the canonical. So you can say that beta is the same parameter. But what about the mu, which is about the alpha? What we can say about the alpha? So for the alpha, we need to pass to the equation which gives you the average of the number of the particles. Average of the number of the particle is that, as you remember, NSL, NRNS. Yes? Just replace it NRS, what I did it here. You can see that this is will be minus partial alpha ln d minus 1 the q on alpha. So this is related to the partial derivative of the q with respect to the alpha. I will tell you one, I will explain you in a very easy method to get the alpha, just from basic terminology. It's not very easy to guess what is the alpha, huh? Yeah. Beta is almost easy because beta is proportional to the average of energy. Average of energy is related to temperature, so we can guess this is temperature. That's not very easy. This is actually alpha is related, the partial derivative of this partition function with respect to alpha gives you the number. So can I say that the alpha is related to the change of the number of the particles? Huh? When, yeah, I want to derive them. So if you have more particle transportations between the system, between two parts of the system, you have more this parameter called alpha. So it gives you the idea that maybe a part of the energy of the system is related not only to the transport of the from the hotter to the cooler part of the system, from hotter to, but it's also related to the immigration of the particle from one part of the system to the other. This type of the energy, we call it chemical energy, huh? Chemical energy. Chemical energy is appear because the balance between the number of the elements in the chemical reaction or any other things is balanced. This balance is broken. Some of the particles immigrate to the other part, so it makes the chemical energy. But, okay, I want to derive this. I want to tell you that the alpha is related to chemical energy, but why? I think we needed one more lecture for this chapter because it remains some things I need to say. Because, for example, now you don't have any idea how to calculate the D, huh? The partition function for canonical, it was very easy, you know? Just make the sigma, or after that you understood that sometimes you need to pass to the integral. For example, for free particles, when you don't have the energy state of the system, or when the energy of the system is a continuous spectrum of momentum or something like that. But here you don't know how to do that. So the rest of lecture I will talk just about the alpha. So next lecture we will see that how to find the D. There is a beautiful relation between the D and the normal partition function, Qn. Qn, not Qn a beta. Qn, just normal Qn. Let's just see. Okay. On interpretation.